Hi everyone, Ross Satchell from Microchip back again. Welcome to episode 12 in our AVR bare metal series. In the previous video, we learned about the registers required in using the ADC peripheral and created an initialization driver for the ADC to use almost all of the available features. In this video, we will finish our bare metal ADC driver by adding functions to control things like enabling and disabling the ADC peripheral, starting a single ADC conversion, starting an oversampled conversion, checking if a conversion is done, checking if the window comparison setting has been satisfied, getting the ADC result, and getting the oversampled result and performing decimation. Then we will write some application code where we will first take a single ADC sample, check whether it is in a user-defined window, and use the USART TX driver that we created in episode 9 to leverage printf to write both the ADC read and also whether it meets the window criteria to the terminal. After that, we will accumulate 16 samples and then decimate so we can increase the effective ADC resolution from 12-bit to 14-bit. Check the window again and use printf to write the ADC value and whether it meets the window criteria to the terminal. So let's get started. Open MPLAB-X and also the datasheet to the register summary in section 33 ADC. So we need some functions to control the ADC beyond the initialization function that we created in the last episode. We will continue using both bit position macros and group position macros in our driver functions. Let's start with an ADC Enable function, which takes no parameters and has a void return. The enable bit was in the ADC 0 control A register, and we can OR equal the current register value with a 1 bit shifted to the left using the ADC Enable bit position macro. Now for the ADC Disable function, which takes no parameters and has a void return. We write to the same register as the enable function, but since we are clearing the bit, we could use the NAND operator, which consists of a bitwise AND and a bitwise NOT, and we would use a 1 bit shifted to the left using the ADC Enable bit position macro. Now let's create a function to start an ADC conversion. I'll call it ADC Start Conversion. The function takes no parameters and has a void return. The start conversion bit is in the ADC 0 command register, and we will OR equal the contents of the register with the ADC Start Conversion bit mask macro. Note that we could also use a 1 bit shifted to the left using the ADC Start Conversion bit position macro. Now let's create a function to stop an ADC conversion. I'll call it ADC Stop Conversion. The function takes no parameters and has a void return. The spconv bit is in the ADC 0 command register, and we will OR equal the contents of the register with the ADC _ spconv bitmask macro. Note we could also use a 1 bit shifted to the left using an ADC spconv bit position macro. Next, we need a function to check if a conversion is done. The function takes no parameters and has an unsigned 8-bit integer return. We need to check the resReady flag in the int flags register. We can use an if statement that checks the resReady bit in the ADC 0 int flags register by bitwise ANDing the register with the ADC _ resReady bitmask. If that resolves to true, we return a 1, meaning the conversion is complete. Otherwise, we return a 0, meaning the conversion is still ongoing. Next, we need a function to check if the window comparison has been satisfied. What I mean by that is if we set the window comparison to check if our ADC read is either lower than, higher than, inside, or outside the defined window, and that condition has been satisfied. The function takes no parameters and has an unsigned 8-bit integer return. We need to check the WinCMP flag in the int flags register. We can use an if statement that checks the ADC 0 int flags register by bitwise ANDing it with the ADC _ WinCMP bitmask. If that is true, we return a 1, meaning the window comparison has been satisfied. Otherwise, we return a 0, meaning the window comparison has not been satisfied. Next, we need a function to return the result of an ADC read. I'll call it ADC Get Result. The function takes no parameters and has an unsigned 16-bit integer return. All it does is return the contents of the ADC0 res register. Now that we've done that, let's write our first application code. In the main function, first I need to set up the clock. You may recall that the minimum peripheral clock that the ADC can reliably prescale down from is 250 kHz. I will use the high-frequency internal oscillator, a clock frequency of 1 MHz, no prescaler, which also means no prescaler enable, and I will output the clock so we can check it as a sanity test. Let's make and program the device and check the clock output pin, which on the AVR64DD32 Curiosity Nano device is pin PA7, and we can see the 1 MHz clock signal on my logic analyzer. Next, let's include our USART driver from episode 9. Let's call the function, and I want asynchronous mode, no parity, 1 stop bit, and 8 data bits. In the USART driver source file, at the top is a define for the baud rate. I will set it to 9600 this time since I'm using a much faster main clock than I did in episode 9. Next, let's add a printf to say driver initialization success. Then make and program the device again, and open Data Visualizer, confirm the COM port settings are correct, and check that the USART works as expected. Next, I will call the ADC init function and pass it the following parameters. vref, reference select is VDD group configuration. vref always on, set to 1. ADC run standby bit, set to 1. ADC conversion mode, set to single-ended group configuration. Left adjust, set to 0, meaning do not left adjust. ADC resolution 12-bit group configuration. Free running mode set to 0. ADC initialization delay set to 16 ADC clock cycles. ADC number of samples none group configuration. ADC clock prescaler set to 2 group configuration. ADC sample delay 0 group configuration. Sample length set to 2 ADC clock cycles, which is the default. ADC mux pos channel A in 18 group configuration, which corresponds to pin PF2. ADC mux neg channel set to ground group configuration. ADC window comparison inside group configuration. Window lower threshold set to 1000. Window upper threshold set to 3000. Next, I want to enable the ADC peripheral by calling the ADC Enable function. Then I will do another printf to indicate that the ADC has been initialized and enabled. Now in the while one loop, I want to call the function ADC Start Conversion. Next, I need to check if the conversion is complete. I can use a while loop in which I check the logical not of the function ADC Is Conversion Done. If it is not done, we stay in the while loop. Once it has finished the conversion, we break out of the while loop. Next, I want to check if the window condition has been satisfied. I can do this using an if statement. In the if statement, I will call the ADC Is Window Satisfied function. If that evaluates to true, then I will printf the window condition is satisfied and also print the ADC result using the ADC Get Result function. If the window condition is not satisfied, I will print that the window condition is not satisfied and also again print the ADC result using the ADC Get Result function. I will add a short delay of 100 milliseconds to avoid spamming the terminal. Now make and program the device and open Data Visualizer. I just left it running before, so I don't need to start it again. We can see the print statement saying window conditions not satisfied and the ADC value is 0. As I turn the potentiometer, we can see the value increasing, and as I cross the lower threshold of 1000, the print statement changes to window conditions satisfied and the ADC value is between 1000 and 3000, which were the thresholds that I used in the ADC init function. Then, as I continue to turn the potentiometer, we can see the values increasing until it is greater than our upper threshold of 3000, and the print statement changes to window conditions not satisfied along with the ADC result. If you've made it this far, congratulations! This is quite a complex peripheral, but we're not done yet. What if you want to increase the maximum resolution of the ADC beyond its maximum of 12 bits? This is where oversampling and decimation comes in. There is an AVR app note that covers this called AVR-121, Enhancing ADC Resolution by Oversampling. I won't go into all of the detail here, but I will cover the parts relevant for this episode. You may recall from your Signals and Systems classes something called Nyquist frequency. Basically, it says that in order to properly sample a signal, you need to sample it at a frequency that is at least twice that of the highest frequency of the input signal. So essentially, you want to maximize the sampling frequency. However, care must be taken when increasing the ADC frequency, as once you progress beyond a certain point in the ADC clock frequency, you will start to see a decrease in ADC accuracy, as the effective number of bits, or ENOB, will decrease. This is something that happens as a result of bandwidth limitations that affect all ADCs. Next is oversampling and decimation. So if you covered this in your Signals and Systems classes, you may recall the theory behind it being quite complex, but the implementation is quite simple. For each additional bit of resolution, we need to oversample 4 times. The equation shows the oversampling frequency being equal to 4 to the power of n, where n is the number of additional bits of resolution multiplied by the Nyquist frequency. Having some noise on the signal helps when oversampling when the amplitude of the noise is at least one least significant bit. Normally, the noise generated by things like the CPU core, I/O port switching, and power supply variations are enough for this method to work. Averaging samples will just result in the initial resolution, but if we added 4 samples together, we effectively gain an extra bit of resolution. But what if we wanted to add 2 bits of resolution to our 12-bit ADC? We would need 4 to the power n, which is 4 squared, or 16 samples. But then we would need to right-shift the result n times, which in our case is 2 times. So let's jump back to MPLAB-X and the datasheet to implement that. I will add a function called ADC Start Oversampled Conversion that takes a parameter called sampNum, being the number of samples to be accumulated, and has a void return. In the datasheet under Functional Description and Initialization, there are some notes. It says, changing the following registers during a conversion will give unpredictable results. One of those registers is control B, in which we set the number of samples accumulated. So in our function, the first thing I will do is call the ADC Disable function. Next, I will write to the ADC0 control B register the samp num parameter bit shifted to the left using the ADC underscore samp num group position macro. I will then call the function ADC Enable and finally call the function ADC Start Conversion. Next, I will also need to write a function to get the oversampled result and perform the decimation. I will call it ADC Get Oversampled Result that takes an unsigned 8-bit integer parameter called ENOB, or effective number of bits, and returns an unsigned 16-bit integer that is the ADC result. I'll create a global variable that will be later moved to a header file and call it BitShift. I will calculate the required decimation bit shift and store it in this variable. In the function, the first thing I need to do is get the current ADC resolution setting, which was located at bit position 2 and 3 of the ADC0 control A register. I will bitwise AND it with the ADC underscore res select group mask, and the result of that I will bit shift it to the right 2 places to put it in bit positions 0 and 1. If that is equal to 0, which is 12-bit resolution according to the datasheet, then the number of bit shifts I need to do for decimation is the effective number of bits that I want minus 12. However, if the contents of the ADC0 control A register bitwise ANDed with the ADC underscore res cell group mask and then bit shifted to the right to put it in bit positions 0 and 1, if that is 1, that means the configured ADC resolution is 10-bit according to the datasheet. Then the number of bit shifts I need to do for decimation is the effective number of bits, or ENOB, that I want minus 10. Then I just need to take the ADC result and bit shift it to the right the value that's currently in the bit shift variable. We're almost done. We need to keep in mind that since we have set the window thresholds, we may need to adjust them since the window compare works on the accumulated value and not the decimation that we have just done. However, I will leave them as they are. Now in our while one loop, I will comment out the function call to ADC Start Conversion and instead call ADC Start Oversampled Conversion and pass it the parameter ADC underscore samp num underscore accumulation 16 group configuration. Then just like earlier, we will have to wait for the conversion to be complete. Then in the if statement where we check the window comparison, instead of printing the ADC result by calling the ADC Get Result function, I will instead call ADC Get Oversampled Result and pass it the number of bits of resolution I need, which is 14. Now make and program the device and open Data Visualizer again. As we turn the potentiometer, we can see the values increasing, and now the window condition is satisfied above 250 and below 750. This is due to the window compare interrupt flag operating on the ADC accumulated value, as I mentioned earlier. Congratulations! You've made a flexible driver for a complex peripheral. Now we just need to separate the ADC code into header and source files like I showed you in a previous episode. So let's quickly do that now. First, let's create a new header file. Right-click under Header Files, then click New, then xc8_header.h and name it adc.h. First, we need the include guard to prevent the header file from being included more than once in a project. Next, we will move all of our forward declarations, also known as function prototypes, from our main.c file to the header file. Now we need to create a C source file for the ADC source code. Right-click on Source Files, then click New, then click C source file. At the top of the ADC.c file, we need to include the ADC header file. Then we need to copy the variables that the ADC driver uses, bit shift. Now we just need to copy the ADC function implementation to the C source file. Finally, in our main.c file, we just need to include adc.h. Recall that we put inverted commas around the header file since it's in the project folder. Now build the project and program the device. Now we can just check that it works as expected as we turn the potentiometer. We can see the oversample and decimated values being read and the window detection working as expected. In the upcoming episodes, we will create an SPI driver for the AVR-DD and send data between two AVR-DD Curiosity Nanos. See you in the next video.